After this section, I would really like to start with the conference work, so let me close this one down. There is four, as you know from the organizational point, we have four speeches today, and we are very, very, very happy that we were so lucky to get our, let's say, TTTech father, Professor Dr. Kopetz, here in-house, and he had, fortunately, had time to come and have a speech. Many of you will know him. He's a legend, I think, worldwide. Anybody in Europe knows him, so I don't need to introduce him in detail. He's the father of the time-triggered architectures and world. And without him, many of these systems would have the problems of collisions and stuff like that today and ongoing. So this is a very, very necessary technology that was found in the University of Vienna. And we are happy that we could start with this production of the networks for it. So I would really very much like to welcome Professor Kopetz to give us his first speech, and I will try to launch this now so that we can have the thing ready. Just a second. Presentations, here it should go. I hope I'm correct if I do it like that. Please help me with a warm welcome to Professor.
Ladies and gentlemen, thank you very much for the very nice introduction. And as you've seen, TTTech is doing a lot of business in many areas. It's a cross-industry company in a sense, and basically focusing on dependability, availability, and safety criticality. Now, I have been working for many years at the Technical University of Vienna, and as a university, you always have to look a little bit ahead of time. And I think the industrial transformation of the technology which we developed at the university into industrial products has been performed by TTTech in a just excellent way. We, personally, well, I'm now already retired from the university, but I'm still doing some research. And I think one of the focus of my research is to look at the complexity of systems. And I'm very pleased that Andreas invited me to give a talk about this topic here. Let me give you a short outline of my talk. After the introduction, I talk a little bit about cyber-physical system of systems, about cognitive complexity, and about simplification strategies, before coming to a conclusion. Let me give you a motivation for this talk. I think the major cost element during the specification, design, operation, evolution and implementation of a large cyber-physical system of systems is in a non-physical domain. What do I mean by non-physical domain? I mean it's mental effort compared to the cost of the hardware. This engineering effort is tremendously high. It's maybe 90%, 95% or 99% of the whole effort of a digital CPS is in the engineering, in the mental part, in the non-physical domain. And as technology moves forward, this part is going to get even smaller, and the hardware part, bigger, and the hardware part is going to get smaller. And the engineering effort depends on the cognitive complexity of a system, of its design, of understanding its behavior. That means how much mental effort is needed to understand the behavior of a system. And if we can reduce this cognitive complexity, if we can reduce the time for understanding, let's say just by 10%, this has a tremendous economic consequence. This is much more important than reducing the hardware by 10%. So, see, cognitive complexity and handling the cognitive complexity is one of the key issues in the future development of systems. It's a research issue that is at the moment, I think, just in its infancy, as you would say, but it's economically extremely interesting. Now let me start out by giving you a short definition of a system of systems. I take the definition from Yamshiri from the University of Texas. And he says a system of systems is an integration of a finite number of autonomous constituent systems. These are basically existing computer systems. They are embedded systems, in our case, by CPS OS, which are independent operable and which are networked together for a certain time to achieve a higher level goal. And the first observation is that system of systems which are happening all around us now. We see many interconnected systems happening. The car is connected to the infrastructure, to other cars. There is a lot of interconnection of systems, and the system of systems are qualitatively different from standalone classical embedded systems. And what are these differences? The scope of the system. Take, for example, the ATM system, the worldwide ATM system. You never know how many ATM terminals there are. The system must be working 24 hours a day, 7 days a week. There are different terminals, there are changes. We don't know how big the system is. The system is continuously changing. It's operating in multiple contexts. It means, take again the ATM, it's operating in Japanese with Japanese language, here in Germany, in English. It's a completely different context. It's continuously changing. The evolution is not, normally we are used to version control. In system of systems, there's nothing like version control because systems are added, are taken away, break down, and so on continuously. The testing, the system is never complete, a system of this size. The testing must go continuously. There's nothing like an acceptance test and say the system is finished and now it's handed over. It's living all over its lifetime. The implementation technology changes. There are terminals in the ATM system, if I take it as a large existing system of different hardware technology, of different software and so on, and they work together in an operating way. Another, what I consider key characteristic is that faults are normal. That means we must expect faults to happen. There's nothing like a fault-free system of systems. And this characteristic that faults are normal has a very deep influence on the design of the system because you must structure the system. You must be concerned about fault containment, about error detection at the interfaces of the fault containment reaches and so on. So this little sentence, faults are normal, has a tremendous influence on the structure of a system of systems. We have autonomous control of the subsystems, which leads to some emergent behavior at the system level. And I'm going to talk a little bit about emergent in a minute. Now, if you look at the CPSOS as a cyber-physical system, there basically we can distinguish between three subsystems: the operator, the cyberspace, which is normally a distributed computer system, and the physical system, which is the engine or the physical environment that is controlled by the cyber system. And if you look at these two spaces, the physical space and the cyberspace, there are fundamental differences. Physical space acts according to the laws of physics. Physical time is the dominant temporal dimension, and the time base is dense. Cyberspace, on the other side, is determined by the program execution, the behavior. The execution time is driving the behavior, and the time base is fast. It is a discrete time. So we need a computational model where physical time and execution time are properly integrated. And I think this integration of physical progress in the physical environment and computational progress in the computational environment is a key issue in embedded system design. And there are many different ways to do it, but one way which I consider to be a very reasonable way to do it is a time-triggered frame-based data flow model. Just to say a few words about this, we partition physical time into frames, and we act with the environment only at the beginning of a frame, or at the end of the frame, which is basically the same. That means the interaction between the computational environment and the physical environment is limited to the edges of the frames. And this model makes it very clear what can be done in the frame in the computer system. It's completely independent of what happens outside, but at the end of the frame we interact. So within the frame, the physical world operates according to the laws of physics, the computer world operates according to the laws of the program, and the interaction occurs at a very definite point in time when the frame finishes or ends. And if you take this model to its extreme, and I think we should do this because it simplifies complexity again, the interaction of the physical world and the computer world happen only at discrete points in times, at the beginning, at the end of a frame. Now if we look at the communication, we have now the interactions. How do we communicate between the different constituent systems, the different embedded system in a system of systems? We have now moved from a single embedded system to a system of systems, and we have two channels of communication. We have cyber channels, and between the different constituent systems form the backbone of a SOS architecture, of a CPSOS architecture. So the interface specification is the key to get a handle on the complexity. So we call the reliable interfaces, there are two classes, what we call the message interfaces, the RUMI, and the physical interfaces, which we call the reliable RUMI. I must state that this conceptual work has been done in the context of a European project I'm still participating in, which is called Amadeus, and we are working on this. Let me say a few words about these communication channels. The message interfaces are, as I said, in cyberspace. They should be standardized, and what we're doing with TTTech and Ethernet, I mean, if you look at the different ways system can communicate, what you do in communication, you actually transform a bit pattern from one space to another space. And so the difference is only in the temporal behavior of the communication system. You can say I do it predictably or I do it event-driven, and this is why we introduced the TTT Ethernet, which combines all these different methods of communicating into a single protocol. So when you need predictable deterministic communication, you can have it. If you need event-driven communication, you can have it, and if you need something in the middle, which is the rate-constrained communication, you can also have it. So we think this protocol essence is the only one you need. You don't need 20 or 30 different protocols, but there is not more than that. Sending data from A to B within a certain time. Now, the RUMIs in the cyberspace, they are very critical for the understanding and behavior of a system of systems, so they should be standardized and they should be really heavily controlled. What happens inside the system is of no concern as long as the standard behavior at the RUMI, at the interface, is given. So as long as the RUMI is not changed, the whole architecture is actually functioning. And this is what's happening, for example, in the ATM system. You have standard interfaces controlled by a standard organization, and as long as the terminals behave according to the standard interfaces, they work fine in the context. Now, since the external world is likely to change, we should not interface directly to the external world, but we should interface to the external world via gateways in order that changes in the external world can be buffered before they come to the critical interface, which is the RUMI. Then we go to the second type of channel, that's the stick merging channel. It's less known, but I think it's at least as important as the message-based channel in cyber-physical systems. The term stick merging comes from biology. A French biologist introduced the term when he looked at the way ants build their nests and behave in the environment. And according to the present understanding, these animals are not communicating with each other, but they're communicating on the basis of traces in the environment. A chemical that evaporates and smells is given out or delivered by one ant, and the next one smells it, and then it travels along the line. And in cyber-physical system, as the merging information channel is present, if one CP one cyber-physical system acts on the environment, which is common to many other systems, and the other CPSs observe the environment. And the information flow is indirectly via the environment, it's not directly between messages one to another. Since the channels operate in the physical environment, this is very important, the environmental dynamics, which is some dynamics coming from the outside world, is part of the stick merging channels, because the environment changes as the dynamics dictate. I'll give you an example later on. So in cyber-physical system, these stick merging channels are extremely important to really capture them, because they often are the missing link in causal loops What we have in many systems is a looping behavior, and the missing link is established by the emerging channels, and these causal loops give rise to emergent behavior, but rather desired behavior. Give you an example of a emerging channel. When two cars operate on the road, they normally don't shout to each other what they're doing. They look at what they're doing and they see what's happening in the environment. This is typically a stigmergic channel, not a message-based channel. And you see already from this that in autonomous driving, stigmergic channels are the most important channels, much more important than the message-based channels. Now the physical interface which uses this stigmergic channel is dynamic. It's an interface that acts from the cyberspace on the entities in the physical world, and the state of the physical world is observed by another entities, and this is where the information flows. The environmental dynamics, that means the changes of the environment which are outside the control of the CPS, is included in the stigmergic channel, and we do have a very, if you get the full picture of what's happening, we need a full analysis of the stigmergic information flow. Let me give you a comparison of the two types of channels. We have the stigmergic channels which go for properties of things, where I have to read, so information transfer is a pull kind. It's only about the present, a direct information mode, no observation delay, and environmental dynamics considered. And on the right side, I have the characteristics of the message-based information flow, which is quite different. I can talk about past, present, and future in a message, but I can only talk about the present in a stigmergic channel. And I say that the most important difference is the environmental dynamics, which is considered in one case and not considered in the other case. So let me now come to the next major section. I talked about complexity. And complexity, I think, is a very general term, and we can classify 4 different types of complexity. First of all, complexity is a property, and complexity is a relation. Now, complexity is a property. We talk about computational complexity, structural complexity, dynamic complexity, and so on. So we look at something, a scenario, and say this scenario has this and this kind of complexity. And complexity is a relation. That means complexity is a relation between a scenario and an observer, or society, in terms of socio-political complexity. So, of course, this classification is not strictly orthogonal. Systems which have a high property complexity and dynamic complexity will also have a higher cognitive complexity. So it's not really orthogonal, but I think it helps to distinguish this. Now what we are interested in is the cognitive complexity. And how long does it take for a human to understand a scenario? And we define cognitive complexity as the mental effort for the average representative of the intended user group to understand the scenario is linked to the cognitive complexity. The time required for understanding will just depend on the purpose of understanding. Normally we're interested in understanding behavior. That's the key, normally. The conceptual basis of the intended user group. If you play chess, a master may understand the board in a second, and the novice may take hours to understand what's happening there. So it's the conceptual basis in the head of the person, the characteristic of the scenario, and of course also the representation of the scenario. So all of this is important for determining the understanding. We talked about TTTech being interested in very much in safety critical system and certification. And this understanding is critical for certification, because how can you certify that the system does something if you don't understand what it's doing? So you really have to understand first before you can do any kind of certification. And that's why I think this is a very relevant research in this particular area of computer science. Now what do we mean by understanding? Let's go a bit deeper. And there's a British philosopher, Gray, who says, understanding means that we have built a mental model that establishes causal links between input, state, and output. If we have developed such a model, we feel we understand. And we know what are the causes for the effects that we observe. And the basis for our reasoning is information, not data. Let me give you a short slide on what do we mean by information and what do we mean by data. Information to me is a proposition about the state of the world, about some state of behavior of the world. And data is a bit better. And information comes about by a tuple of data and explanation of the data. So that means the data is a bit better generated by a sensor, and if we know the design of the sensors, we know how to explain the data and come to information about some property of the state of the world. What is interesting is, if you look at it that way, that when data is carried explicitly in a message, the explanation is often derived from context. And if we have two different contexts in a system of systems, one, let's say, in the US and one in Europe, and they use different standards, like in temperature, the same bit pattern as data can reside in different information at the two ends. And so when we come into a system of systems in general, we have to be careful this context sensitivity of data, and I think the information, we call it an item, an information item, is a much more general term than the term data, because data, as I said, is context dependent. 86 degrees Fahrenheit mean the same thing as 30 degrees Celsius in one day. See, the data is context dependent. The content, the information content, the information is not. So what are the consequences of this insight? The consequence is that some input and output items must be observable at the interfaces. So observation, and we must observe items and not only data. We must know how the data has to explain the interfaces. In case the internal state is determined for understanding, as implied by the notion of understanding by Craig, we also must make the internal state visible at the interface. That's again a design criterion. Another point is that causal order presupposes temporal order. That means if A causes B, A must be before B. And so we must have a clean notion of temporal order of all events. Now if you take the frame-based model, we do have a very clean temporal order of the events in the environment. And of course, if you have a global time in the system, then the temporal order can be established easily, and this is the prerequisite for the causal order. And this brings us to the need for a global time in a distributed system. I think a dependable time, and it must be dependable because I don't want to have a single clock which can bring the system down. It must be fault-tolerant time. Is needed to understand the temporal behavior of an SOS. It's needed to interpret the timestamps, to control or synchronize the durations of the frames which are introduced, specify temporal properties of interfaces, synchronize inputs and outputs, synchronize the merging and message-based information. It's very important because we have to get the full picture of the environment, which is the fusion of message-based and stick merging information, but we have the fusion at the right time. Otherwise, we get different. Okay. Allocate resource conflicts, also conflict-free, for example, time-to-time protocols, prompt error detection, and we can strengthen security protocols. Now, look at systems, and this is a really an example which I like to take. What happens that there was a big power blackout in the US 2003, and then the power was lost in northeastern US for a few hours, many hours, and 8 hours. And in the report it says, if they would have used global time, things would have been a lot easier. You can read it yourself. So, coming to complexity, how much valuable engineering time has been lost by not using a global notion of time in the system? So now let's come to the simplification strategy. How can we simplify a design? And how many minutes? Well, there are 4 principles, 4 strategies which I would like to mention here: abstraction, emergence, partitioning, and segmentation. Now, abstraction means I take something away and make the system simpler. So I have a viewpoint, and the viewpoint normally, as I said, is behavior. So how can I reason about the behavior without having all these details available? And in cyber-physical system of systems, the reasoning is on interface behavior. So I don't care what's happening inside the system, I only look at the interfaces. And if the interfaces are very specified, I should be able to explain what's happening. Abstraction is important to get simpler models, because I think something in this is get simpler, and it establishes a hierarchy. And I can talk a lot about hierarchies, but I don't have the time to do that. And the hierarchy forms categories of higher levels, and a category which is interconnected with other categories is basically a concept. So concept formation is very much based on the proper abstraction. And the concept is nothing else but the theory about a certain class of entities. So, key to successful abstraction, cellular mechanics. If you look at the world as a single mesh point, that's the ultimate abstraction you can have. You forget about everything else, you just see it as a single mesh point. That's an ultimate abstraction. This gives you the power to handle all these heavenly bodies in a proper model. If you would look at all the details of the world, you would be lost in complexity. As I said, the interface abstraction in a system of systems, in any system, I think also in the work you're doing, is probably the most important abstraction that you have to be caring about. You have a behavior at the interface, that means how states evolve over time. If you have a time-space data model, the behavior is a sequence of temporal data and information, of course. And you can abstract from the internals of a constituent system if you use this. But what the problem is that many interfaces are not properly specified in the domains of time. We are normally only interested in specifying value domains, data types, and so on, but temporal domains are often needed. That is why I think the time-period architecture and time-period protocols help you to specify the temporal aspect of interfaces. It's needed for a complete specification, particularly if you then start causal reasoning and so on, you need the time. So we have three different types of systems to interface with. I think the most important one are the open constituent systems which interface with the environment. They have environmental dynamics to see, and we have to have a model of the environment as part of the interface specification. I have now a PhD student who works on interface specification of constituent systems. And the classical specification which you get in all these SOAP and so on, all these the service-based architectures, they are concerned about data types and data structures and so on, but when it comes to the real semantics, the meaning of the data, they all break down. Forget about it. Let me go to another important topic, and that's emergence. A phenomenon of a whole, of an interaction of system, is emergent at the macro level, or the system level, if it's new with respect to the non-relational phenomena of any of its proper part at the micro level. I mean, there is new phenomena which get at the higher level which are not part. A very simple example of a new phenomenon is deadlock in computer systems. You have independent computer systems that operate fine, and you put them together and all of a sudden they stop. That's bad emergence, but it's emergent behavior. But there is also good emergence, and good emergence I think is the thing we want. The interaction of parts calculates a new whole which is characterized by new conceptualization. Take, for example, in clock synchronization, the concept of a fault-tolerant time base. It's a new concept which is generated by the interactions of the clocks, and it's a new conceptualization. I don't worry about time anymore that anything fails. I think time is available independent of the working of the crystals in the different nodes. And this comes about by the interaction of the clocks to generate a fault-tolerant global time base. Now, as I already mentioned, there are different types of emergence. They're expected and unexpected, or explained and unexplained, but it's a bit more difficult, and it can be beneficial and detrimental. I've given you two cases: fault-tolerant clock synchronization as a beneficial case of emergence, deadlock as a bad case of emergence. What I would like to focus now on the beneficial case, because this is a real simplification, a strong simplification technique. Now, there are two properties of emergent systems, convenience properties, and they say a given emergent phenomenon at the macro level can emerge out of many different arrangements of the parts at the micro level. Take, for example, the Boolean logic. In Boolean logic, I look only at the transistor switching function true, false at a certain time, and then I in a very simple word. If you would have to look at every transistor, how the atoms are situated in the crystal, in the bulk material, how the dopants are situated, it would be impossible to reason about what's happening there. So the transistor effect is an emergent effect. I conceptualize it and abstract it in Boolean logic, and all of a sudden the world gets simple. And I think we have to look for this new conceptualization of emergent effect to simplify. And the two supervenient properties give you this. The first one says, as long as there are many different arrangements of atoms in a crystal, as long as the switching function is maintained, I forget about it. I can reason about it. And this is what supervenience 1 gives you. Supervenient 2 says something, if at the higher level something is wrong, something wrong must be at the lower level, something different. So the second one is powerful for conceptualization and simplification. The first one and the second one is powerful from the point of view of failure analysis. Because failure analysis I go to supervenience 2. So the proper conceptualization of emergent phenomena can lead to an abrupt simplification at the next higher level of the system thinking. And there are many cases, for example, if you look at in databases, you introduce pointers, and all of a sudden the pointer is a new conceptualization. You don't look at the big pattern anymore. Or you look at Boolean logic, and I gave you another case for the gas theory. The second important principle, the third one, two, abstraction and dimension. The third one, which there's a whole book written about this by Soon, about this principle, is partitioning. There are many names for partitioning. It's called divide and conquer, separation of concerns, functional independence. But the basic idea of partitioning is independent functional requirements should be implemented by independent mechanisms. You don't want to link too many things together because then it gets difficult. The separation of concerns leads to mechanisms that can be analyzed in isolation without any complication caused by the entanglement of mechanisms. Let me give you again an example. The communication, the time-triggered communication. Normally communication, event-triggered communication, which is used in many systems, the temporal structure in event-triggered communication is dependent on the behavior in the data domain. Then when the task is finished with the data finished, you send the message. In time-triggered communication, the instance of sending a message are independent of the data, they only rely on the progression of time, which is predictable and known. So I have decoupled, I have partitioned the data domain from the temporal domain, and I can now reason about the temporal properties of a communication system independent of the behavior of the data transformation in the node. So this makes it a lot simpler. As Andreas has shown you, we've been quite successful in a number of safety-critical applications in the aerospace industry, and in space industry, this probably is one of the critical issues. We can prove the properties of the communication system independently of the properties of the data transformation. And you cannot do it, otherwise you entangle it and it gets much more important. That's a classical example of partitioning, of the advantages of partitioning. Okay, there's another example of partitioning is in the interface abstraction. That if I use a sensor to capture the environment, I want to get the sensor information, the items in a standardized form which the user understands, which the user is familiar with. So I want to hide the idiosyncrasies of the sensor in a particular software module, and in the interface of the sensor I want to give to the user a representation which the user already knows in the standard physical measurement system or whatever. And again, this is an example of partitioning, of using the idiosyncrasies of a sensor at the sense level. Now the fourth technique of simplification, which is often overlooked, is segmentation. Segmentation refers to the sequential split up of actions in the temporal domain. So if I have a clean segmentation, I can go through a behavior step by step and can reason about the behavior at each step, only looking at the environment which is particular at this step. Of course, in order to do that, I have to have a clean separation between physical and cyberspace behavior, and this is achieved by the frame-based data flow model. Now, the well-defined temporal order of events supports the causal analysis of phenomena which are needed to understand the phenomena. Now, if we have concurrency, and I know that your project is looking about concurrency in processes, then the situation gets much more difficult and much more involved. If you have a clean separation of physical and clean separation of the processes and can segment them, look at them one after another, things get a lot simpler because I only have to consider at a particular point in time the immediate environment of this particular action. Example of the segmentation: in control system, you do a loop analysis and you see that a loop at one and another point and can, at these discrete points, reason about the behavior as it time progresses. Then we come to the summary. Here I summarize the simplification principles that you use in the design of cyber-physical system of systems. Use global time, divide and conquer with partitioning, try to conceptualize emergent behavior, use time-triggered communication to get temporal order, focus on the relied upon interfaces, and don't forget to look at the interface state. So I'm coming to the conclusion, and they say every reduction of the cognitive complexity of a large system is of utmost economic significance. And if you can apply some of these rules and simplify the understanding of the systems, it's real money as a payback. It's not something academic only. So we have to establish the requirements for these mental models. Temporal order is a precondition for causal order, and this gives us then the basis for reasoning and the simplification strategy.